Hello, welcome to Mickey Techie. Learn as engineer, teach as champion. First of all, I would like to thank my family for their continuous support and encouragement of creating these kinds of technical videos in public domain. And I would like to thank my mentor, Professor R. Surendran from Government College of Technology, Coimbatore, for igniting me a spark of creating these kinds of technical videos in public domain. And I would like to thank Almighty, my God, for my good health and broad mind. And I would like to thank my friends, followers, my dear students, and subscribers for their continuous support and encouragement. Today's topic of interest is properties of the fluid. First of all, we have to know what is meant by fluid. And we have then after we have to know what is the properties of fluids which in which the real as well as the ideal fluids are in use. Before that, I will start with the quiz. We are going to recall some of the dimensions and the SI units of the quantities which are displayed here. Let us see the figure 1. What it means, it is the distance between A and B, or a time taken to travel the distance between A and B. So this is here we can recall the length. Distance between the 2 points is called as a length, and time to reach from point A to B or B to A, it is time. So the fundamental dimensions of length and time with this figure we can understand. So what it means? It is a quantity of rice bag. It is mentioned in mass in terms of kg, length in meter, time in second or minute or hour, whereas quantity of rice bag is in terms of kg. Next, it is a temperature. We can see the image. We can easily predict it is a temperature, the degree of coldness or degree of hotness. So that is the meaning. So from these diagram, we have to know length of meter and mass of kg and time of second and temperature of degree Celsius or degree Kelvin. Okay. Next, have some of the useful working definitions. Dimensions. Any physical quantity is being characterized by dimension. If we can say the quantity of rice bag, that is called as a dimension. So mass is a dimension. The unit, the magnitude assigned to the dimension is called unit. In the same case, the quantity of rice bag is a mass. The unit of the mass is kilogram. If in terms of Newton we want to know, we directly multiply the kg into kg with then acceleration due to gravity 9.81, we directly get Newton. So the magnitude assigned to the dimension is called units. Therefore, the basic dimensions such as mass, length, time, and temperature are being selected as a primary or fundamental dimensions. So these dimensions are fundamental for all. So here the secondary dimensions or derived quantities, derived dimensions, it is nothing but a combination of the fundamental dimensions. We can say the velocity, the unit of velocity is meter per second. So here length come into picture and time come into picture. therefore time in terms of -1. So this dimension is called as a derived dimensions. It is a combination of the uh, fundamental dimensions. If we can say the volume, it is in terms of meter cube, that is L power 3. So 3 times we are multiplying the length. That is why it is called as a derived dimension. Okay, I hope you have understand what is meant by a primary or a fundamental dimension, what is meant by secondary or derived dimension. So next, we're going to write some of the symbols and the SI units of the picture shown here. We have a six more pictures. Let us see. The velocity, it is in small v, and it is denoted by an SI unit of meter per second. And this is the volume, it is mentioned in capital V, and this is in meter cube. Next, it is an acceleration, either A or G. It is 9.81, generally acceleration due to gravity, meter per second square. And weight, we are mentioned in a W, capital W, it is in Newton. Weight is in Newton. Next, it is a pressure mentioned in P, that is a Newton per meter square. Worker energy W in terms of joules, joules or Newton meter. Like that, we can give the symbols as well as the SI units. Here, we have to know the definition of stress. Generally, stress and pressure are in unit wise it is an analogous, but is we have to know the difference very clearly about that. If you can say the pressure is the force per unit area, whereas the stress is the resistive force per unit area. So pressure is an applied force and the stress is an force produced by the body. So that is the difference between the stress as well as the pressure. We can develop the pressure, but in order to maintain the pressure, or in order to control the pressure, the material which is subjected on the pressure will produce an internal resistive force or internal resistance, that is called as an stress. Generally, in mechanical, the stress is an important phenomena on every design aspect, whether it is a solid design or an fluid design. It is very, very important. The stress is nothing but the resistive force per unit area. And we have two different types of forces can be acted in the body. One is normal force, which is the force acting normal to the area, that is called as an normal force, where the force acting along the plane of the area, it is called as a tangential flow force. Let me explain. So consider this is a body. So here it is an area. Okay, so this is an area. So if the force is acting like this, so this is called as an normal force, or say this is a body. So here it is fixed, and along the area, if it is acting along the area, it is acting either in this direction or in this direction, then it is called as an tangential force. I hope you have understand. In fluids, the tangential force is very, very important. That is, the tangential force always produce shear. So, the in fluid, the shear stress is very, very important than the normal forces and normal stresses. So, we have to concentrate on this tangential force. So first, we have to know what is the definition of the fluid. If any substance, if any substance which deform continuously under the influence of shear or tangential force, it is called as a fluid. A fluid is a substance. It doesn't matter that how the quantity of the shear stress, even very small amount of shear stress can make the fluid to deform continuously. So that is called as a fluid. If any substance with the help of any shear force, either it is a small force or a large force, when the body deforms continuously, then it is called as an fluids. So say here, in the solid, if the shear force is acting, it may deform up to the elastic body, and if the shear stress is withdrawn, it can regain its original position. Whereas fluid doesn't do like that. If any small quantity, there is no elastic and there is no plastic property when the shear force is applied on the fluid, even a small amount of a shear force can make the fluid to deform continuously. It cannot regain its original position after removal of the shear force. So that is the definition of the fluid. Here we have to know that the terms which they have given is very beautiful. In solids, the stress is proportional to the strain up to its proportional limit, or we can say up to its elastic limit. The stress is proportional to strain. It was derived by hooks, and whether the fluids, the stress is directly proportional to shear strain rate or change of strain with respect to time or velocity gradient. This was postulated by Newton. So Newton's law of viscosity, which is very important, it depends on the stress and rate of strain or velocity gradient or shear gradient, we can say, or strain rate, rate of strain, whatever may be. So the shear stress is directly proportional to rate of shear strain. These fundamental uh, difference or fundamental proportionalities is derived by Newton, and the law is called as Newton's law of viscosity, which is very important for in the fluid mechanics. From the Newton's law of viscosity only, the term viscosity has been derived. So it is a one type of a property. We will discuss that property later on slides. So next, what you can understand by this picture, I can say, so this is a solid, so this is a liquid, so this is the gas. Okay, how I can mention this? If you can see, the atoms are well arranged and closely packed. In the liquids, the atoms are closely packed, but it can it is having a freedom to move or freedom to occupy the any shape. And here, the gas, the atoms are randomly arranged. So it have a privilege to get closer to the atom, and also it can also occupy any type of volume in nature. So here it is a solid. Solids are closely packed. The particles are very closely packed. The particles are tightly fixed in one position, making it hard to separate them. So the solids are having a definite shape and volume, where the liquids, it doesn't have any shape. It does not have any shape by own. It can take the shape of the container where it is being used. They are not easily compressed or expanded. The same volume no matter what the shape is. So that is the property of the liquid. Where the gases, it can change the volume very easily. The volume and shape of the gas is the volume and the shape of the container is being converted. Okay, so here the difference between the solid, liquid and gas, here you have to notice this thing. Okay, in solid, It is a rigid, fixed shape, fixed volume, cannot be squeezed. Cannot be squeezed. In liquids, no rigidity, no fixed shape, but fixed volume, it is also cannot be squeezed. Whereas in the gases, it is having no rigidity, no fixed shape, no fixed volume. Therefore, it can be squeezed. Squeezing means it can be compressed. It can be compressed. So here we are going to start the properties of a fluid. In the properties, the first and foremost property is the density or mass density. In the definition, it is the ratio of mass per unit volume of the substance, which is called as a density. So it is denoted by rho. Rho is nothing but mass per volume. The unit is kg per meter cube. We have to know that density of water is 1000 kg per meter cube at 4 degrees Celsius, and density of mercury, which is nothing but 13,600 kg per meter cube, and density of air, which is 1.21 kg per meter cube. This you have to understand very clearly. So these water, mercury and air are the standard substance which we have to know it very clearly. Okay, so this is the very simple illustration of the density. By the arrangement of the molecules or the atoms, if it is having very closely packed, then we can say the substance is having a high density. When it is free to expand or contract, or the intermolecular gap between the molecules, then it is having low density. So with this, as I mentioned above, the air which is having 1.21 kg per meter cube, and whereas the mercury it is having 13,600, so it is having very closely packed atoms. For the better understanding, if you can able to answer this, and you will get you can understand the density better. So here we have a six components: so oil, sponge, iron bar, water, wood, and air. We know that we have to arrange in the descending order of a high density to low density. We know that iron bar is number one, and water is number two, oil is number three, wood is number four, and the sponge is number five, and the air is number six. So like that, we can arrange by means of the density. Next one is the specific weight or a weight density. What is the weight density? It is a gravity multiplied by the density. That is nothing but specific weight, which is nothing but rho into g. That is, we know that density is equal to mass by volume. So mass is multiplied by the gravity. Therefore, it is called weight by volume. That is why it is mentioned. So small w, the specific weight, which is equal to rho into g. Here we know that for the standard substance water, it is 1000. It is 1000 into 9.81. Therefore 9810. The unit of the mass density is Newton per meter cube. We know that mass into gravity, so kg into meter per second square, it will become Newton. So here you have to know one thing. Newton is equal to kg meter per second square. Therefore, it is m l t power minus 2, which is the fundamental dimension. In terms of fundamental dimensions, you can mention the specific weight as like this. Here, next one is the specific volume. It is the volume of the fluid occupied by unit mass. It is the inverse of density. So it is the specific volume in this small v. It is volume by mass It is nothing but 1 by rho. So inverse of the density is called specific volume. So the unit is meter cube per kg. Okay. Next is the specific gravity or relative density. It is the ratio of weight density of the fluid to the weight density of the standard fluid, or density of the fluid to the density of the standard fluid. Here in the liquids, the standard fluid for liquids is a water, and for the gas it is air. So this thing you have to notice that. And the specific gravity doesn't have any unit, because the numerator and denominator are the same quantities, therefore the same units get cancelled, so it is having no unit. So from this figure we have to understand that for the 1 kg of mercury, say 1 kg of the mercury, we need a 13.55 kg of water. Therefore, if we want to know the specific gravity of mercury, the density of mercury is 13,600 divided by density of the standard fluid is water, it is 1000. So it becomes 13.6. So density specific gravity of the mercury is 13.6. What it means that in order to maintain the same weight, we need a standard fluid into 13.6. Okay. So next is the viscosity. So viscosity, the property viscosity is derived from the Newton's law of viscosity, where the relationship, like the shear stress is directly proportional to the rate of shear strain, that is du by dy. This proportionality constant is viscosity. The proportionality constant is viscosity. Definitely, on any real fluid which should possess viscosity, whereas in the ideal fluid, it have no viscosity, and it is not in compressible in nature. So 1 by k is nothing, and the surface tension, there is no surface tension. So both all are zero, like that. Okay, so here the viscosity, it is the resistance offered by a fluid against motion, which is called viscosity. We know that the viscosity is the resistance. It is simply like a friction, the fluid friction, which can, for the better understanding, in the inter friction between two layers of the fluids, which is called viscosity. It is denoted by mu. The unit is Newton second per meter square. We know that Newton per meter square is equal to Pascal. So it is indicated also in Pascal seconds. Pascal seconds, or sometimes poise we can say. So 1 poise is equal to 1 by 10 Newton second per meter square. So this you have to understand. It is also defined as shear stress required to produce unit rate of shear strain, that is called viscosity. Therefore, from this definition, the viscosity is equal to shear stress divided by, so du by dy. Therefore, tau is equal to mu into du by dy. The proportionality constant between these two is nothing but viscosity. So from this definition, we can betterly understand the formula for the viscosity. If we know the term viscosity, we have to know the kinematic viscosity. The kinematic viscosity, it is in nu, it is nothing but viscosity by density. Viscosity by density. It is given in Stokes, or meter square per second. 1 Stoke is equal to 10 power minus 4 meter square per second. So this you have to understand. And this viscosity is also be called as coefficient of viscosity, actual viscosity, uh, dynamic viscosity, like that. We have different names. So you have to understand better. So from this figure, we know that a fish is moving in a water and a bird is flying in an air. So the bird can easily flying, whereas in the fish it is not easily move because of the viscosity difference between the air. Here you have to understand that if the temperature is increased, if a liquid temperature is increased, the viscosity will get reduced. For a gases, if the temperature increases, the viscosity will get increases. So here also one thing you may experience is that by stirring of a water and a stirring of a syrup, we know that the stirring of a syrup or an oil, it is bit difficult than water. Therefore, the viscosity of syrup is more than water. From this, we can understand that. And next, at the high viscosity fluid, if a fluid is having high viscosity, if you heat for some times, the viscosity will get reduced. Like that, if it is in a cold substance, say in the water is in a 0 degree Celsius, it will become a solid. So the viscosity will become 0. So no flow is there. You know that the solid will not flow. If it is converted into a slow liquid of 4 degrees Celsius, it will move a bit. A slow movement is there. If if it is in the 100 degrees Celsius, it can move faster than it is in 0 degrees Celsius or our room temperature. So that we have to understand. By means of a heat, the viscosity varies. Here, as we longing for this Newton's law of viscosity, the shear stress is proportional to rate of change of velocity with respect to y. It is denoted in tau. You know that tau is equal to mu into du by dy. So this is the Newton's law of viscosity. If any fluid, if any fluid will obeys the Newton's law of viscosity, it is called as Newtonian fluid. If it does not obeys the Newton's law of viscosity, it is called a non-Newtonian fluid. That you have to understand. The next is the kinematic viscosity. It is the ratio of dynamic viscosity to the density of the fluid. It is denoted by nu. So nu is equal to mu by rho. Next, what you have understand from this figure, one, say we are going to take a syringe. In the syringe we are filling with an air first, so it can be compressible. If it is in a water or if it is a sand, we cannot compress. So from this figure we have to understand the property that is called compressibility. The compressibility is an inverse of bulk modulus. We know that compressibility is inverse of bulk modulus. It is denoted by K, and beta is the compressibility. So what it mean? Bulk modulus, K, direct stress or hydrostatic pressure to the uh, volumetric strain, that is change in volume per original volume. So this is the formula about the bulk modulus. The compressibility is the inverse of bulk modulus. So here the compressibility is the reciprocal of bulk modulus of elasticity K. It is defined as the compressive stress to the volumetric strain, or bulk modulus we can say increase in pressure to the volumetric strain, as I given already. The unit of bulk modulus is Newton per meter square, whereas the compressibility is inverse of K. The unit of compressibility is meter square per Newton. So that is the difference. So here the picture is gas we can easily compressible, whereas the liquid we cannot compressible. Okay, so what you have understand from this figure? Water droplet formulation on the smooth surface, like a feathers of a flower or a leaf. or inside that the insert walking on the water surface, and also the razor blade is floating on a cup of water. What it mean? What the property you have remember? Yes, it is a surface tension. The force acting on the molecule of a liquid, which is called as a surface tension. So it is a material property whereby a liquid at the material interface, usually liquid gas exert a force per unit length along the surface. It is called as a surface tension. It is denoted by a Greek symbol of sigma. The unit is Newton per meter. And you have know that in a water, then oil is floated. If you can see the water oil interface, you can definitely know that how the surface tension is been acting on the water oil interface. Next is a cohesion and adhesion. When I say cohesion, the same molecules are attracted, which is called cohesion, whereas the different molecules are attracted, which is called adhesion. So like this, in adhesion, we have a concave meniscus. In cohesion, we have a convex meniscus. For concave meniscus, the water is a very good example. The convex meniscus, the mercury is a very good example. Okay, so what you have understand here, a tissue paper is dipped in the tea or a cup of water. What happens? The water will rise on the paper. And similarly, a lamp, a lantern lamp is glowing. How the oil came up and how it glow by means of a term which is called capillarity. And also similarly, a sap of a tree, how the roots are capture the water and it transfers to the leaf. It is by means of a capillarity. The interesting sequence of surface tension in the capillarity effect, which may rise or fall in the relatively small diameter of the tube is inserted, that is called as a capillarity. It is related with surface tension. We can say mercury in glass, as we already discussed, the convex meniscus will produce capillary depression, where water in the glass it have a concave meniscus, so it is capillary rise. In capillary depression, cohesive force is greater than adhesive force. In capillary rise, the adhesive force is greater than cohesive force. This can be postulated by means of a formula, that is H is equal to 4 sigma cos theta divided by rho GD. So the diameter is important and surface tension is important. This capillary height, which is directly proportional to the surface tension, and capillary height which is inversely proportional to diameter. What you have to understand is, if the surface tension increases, the height increases. Where the diameter increases, the height will decreases. This you have to understand very very clearly in nature. For the mercury, this theta value is 130 degree. For the oil, for the water, the theta value is 0 degree. This you have to know better. So with this, I close the properties. If you have any doubts, please let me know in the comment section. I will make another video for clarifying your doubts. If you are interested in this video, please like, share and subscribe the Mekiteki channel, Mekiteki with Santhosh channel, for your better understanding of mechanical engineering. I hope I have given enough knowledge about the property of fluid. So with this, I am closing the today's session. And thank you all. Thank you for the patient listening. Bye bye from Santhosh. Thank you.